Hello everyone, welcome. My name is Shona Nirikala. Today I'm here to explain real numbers of Maths Class 10 NCERT textbook. So without any further ado, I would like to start the video. So let's go. So let's start the chapter Real Numbers. You might ask me the question, what are real numbers? Well, I know, but if you don't know, don't worry, you don't need to be tensed. Here, I'm going to explain it to you today itself. So, the topics we are going to cover from this chapter are the fundamental theorem of arithmetic and revisiting irrational numbers. You guys are really lucky that you got two topics deleted. Euclid's division lemma and terminating and non-terminating decimal numbers. Lucky. Now, on to our question. What are real numbers? Real numbers are positive numbers. I can say numbers. There's another term called integers. So, another way, real numbers are positive integers, negative integers, irrational numbers, and fractions. These are all examples. If one asks you, what are the examples of real numbers? You should say this answer. So these all bunch of numbers includes in real numbers. We can say that a number is a real number except for complex numbers. Now you say, hey, you said real numbers are just simple numbers like positive integers, negative integers. Now you come with complex. The word complex means not every single numbers. There are like 1.75. Is it kind of difficult to solve decimal multiplication addition? I know, I struggled with it too. So they are called as complex numbers. So there is 1 by 2, minus 1, root 2, and these are all the examples of complex numbers, and these all includes in irrational numbers. So in general, real numbers constitute the union of rational and irrational numbers. Here you can guys see a flowchart of real numbers. We see that real numbers are made into two, that is rational and irrational numbers. From rational itself, also rational can be represented with the letter capital Q. Now there are two types of rational numbers, non-integer rational number and integers, which is also called as capital Z. And again, integers are constituted into two types, that is negative numbers and positive, not positive, whole numbers. I'm mistaken. Whole numbers is also represented as W. Now, whole numbers and natural numbers, they are kind of confusing, right? Whole numbers starts with the digit 0, while the natural numbers just start from the digit 1. Now, going on to our main topic, fundamental theorem of arithmetic. The key ingredient of fundamental theorem of arithmetic is prime factorization. You need to master the prime factorization method, and it can include LCM and HCF. The LCM is known as the least common multiple and HCF is known as the highest common factor. Here you can see an example. 2 multiplied by 2 multiplied by 3 multiplied by 3. So there is 2 2's and 2 3's. Now the definition of fundamental theorem of arithmetic is here. Every composite number can be expressed as a product of primes, and this prime factorization is unique apart from the order in which prime factors occur. So this is our first question. Let's start. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to the product of two numbers. So the numbers are 26 and 91. So it is obvious that we have to do prime factorization. So 26 is the multiple of 13 into 2. and 91 is 7 into 13. So that is what specifically it is written here. So from that we can see that 13 is the common multiple. So the HCF it can be 13, and the LCM we have to multiply 13 into 2 into 7, so that will be 182. Now they have said that LCM into HCF. So we have to do LCM, that is 13 into 182 is equal to 2366. Now if LHS is equal to RHS, we have to prove that RHS is also equal. So we have to multiply 26 and 91, then also we'll get that it is 2366. So hence we can say that LCM into HCF, it's a product of 26 and 90. Let's do this question. It is the other way of doing. From the other question we have learned that LCM into HCF is equal to product of two numbers. Here they have given LCM, we have to find the LCM, and they have given the HCF of 306 and 657, that is equal to 9. So by taking the LCM part as x, 9 into x is equal to 306 into 657. So we have to divide 306 into 657 by 9. Then we will get the LCM 22338, 22,338. Now let's do this other question. It is included in our textbook and it's also important. So when a digit should end with 0, it has to be multiplied, or it should be divisible by 5. So the unit place should contain 0 or 5. So 6 is equal to 2 into 3. So that it's not divisible by 5. So from that we can say that for any natural number n, 6n is not divisible by 5, and thus it is proving that 6n cannot end with the digit 0 for any natural number n. Now let's understand this question, which is also very important. Explain why 7 multiplied by 11 multiplied by 13 plus 13 and 7 multiplied by 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1 plus 5 are composite number. So from the first part we can take 13 as common. Then we'll multiply 7 into 11 and 13 plus 13. So taking 13 as you can see here, so that will be 13 into 78. So the composite number has two factors. It is composite number should have more than one factors. So here it's 2, so it's a composite number. Again in this we can take 5 as common, and multiplying it will be 108 plus 1, because we have to substitute the other number. So it will be 5 into 1009. So both of it are composite numbers. Now on to our second topic, revisiting irrational numbers. So there are many examples of irrational numbers. As from the textbook you can see there are many proof questions. All the proofs are same just for the numbers. When you square them you have to change it. Like for root 2, if you do squaring it will be 4. When it's be root 5, to prove root 5 is an irrational number, it's gonna be 25. When it's 7, 49. So the pattern changes, but the steps all are same for every single question. So you don't need to worry. Now let's also see a really important question. So I told that if root 2 or root 5 comes, just the squaring is different but the steps are same. So the question is, prove that root 7 is irrational. So first you have to assume that root 7 is rational. Then we can say that root 7 is equal to a by b and a is equal to b root 7. Then we have to square on both the sides. That will be a square is equal to 7b square. Now a square is divisible by 7 and a is also divisible by 7. Then other way we have to prove it. We can say a is equal to 7p, and we have to square it again, and we will get, see, this where it gets a little bit tricky. 49p square is equal to 7b square. So here b square is equal to, we are cutting it, so b square is equal to 7p square. Here b square is also divisible by 7 and b is also divisible by 7. Now the proving is done. Now for the concluding part, we can say that a and b have least common factor, that is 7, but this contradicts the fact that a and b are co-prime integers and our assumption is wrong. So we can say root 7 is irrational. I hope you guys have understood the lesson number 1, real numbers. Now, if you have doubt in the second chapter, I'm coming again with the video of polynomials. Stay tuned. Bye.